This video is designed to help you prepare for the AP test. It is not sanctioned by or made by the College Board. It's on liquids, solids, and solutions. You can read the learning objectives on the screen. Let's talk the liquid phase or liquid state first. Liquids differ from solids and gases by their intermediate potential energy between those of solids and gases. As gases liquefy, or liquids boil, their kinetic energy does not change. Thus, the temperature does not change. The potential energy is changing. The boiling point is the temperature at which gas forms throughout the liquid because the vapor pressure is equal to outside pressure. If outside pressure is 1 atmosphere, then at 100 degrees, for instance, water boils. Some alcohols boil at lower temperatures than that because they have a higher vapor pressure at each temperature. Thus, boiling point depends not only on the substance but also on the atmospheric pressure holding the molecules of the gas as liquid. Here is a warming and cooling curve for water, and you can see as you go from left to right the progress of the warming or the cooling and the temperatures involved on the vertical axis. What we're trying to do here is, at least for the solid, liquid, and boiling situation, we're trying to give you an idea of where each one of the formulas you'll use is used. For instance, here with the warming solid and here with the warming liquid, you use your familiar MCAT formula, mass times the specific heat capacity times the change in temperature. But here, when you see either melting or freezing going on, delta H is equal to the mass times the delta H of fusion. Now, as you're going up, the processes are endothermic, as you're making things into either higher kinetic or potential energy. When you're coming back down, here was you're cooling a liquid, and here, of course, where you would be freezing the liquid water, and here where you would be cooling off the ice that results, you have exothermic processes. So here's a problem that you probably won't run into in the AP test, but it certainly is good practice. Ice at -5 degrees Celsius is warmed until it boils away. If its mass is 122 grams, how much heat has been added while doing this? Here are the formulas, and here's the chart, and here are the specific heat capacities, either in joules per gram Kelvin or in joules per mole Kelvin. And so why don't you turn this off and simply stop the video and then do the problem as far as you can with the numbers that you have, and then turn it back on so that you can see the results. So let's start off with this problem. If we warm ice, we are increasing the temperature, in this case by 5 degrees, from -5 to 0, and we will use the specific heat capacity of the solid water, that is the ice. And you can see here it's 2.11 joules per gram Kelvin. When you use the MCAT formula, you will see here you come up with 1287 joules on your calculator. If there are two significant digits here, that means 1.3 kilojoules. If there are three significant digits, of course, it would be 1.29 kilojoules for the 122 grams. The second thing you have to do is turn the ice into a liquid. This is, of course, melting, and the temperature does not change. So you use simply the delta H of fusion times the number of grams of ice that is turning to liquid, and you get 40748 joules, and when you change that to 3 sigdigs, you have 40.7 kilojoules. The third stage You are warming the liquid from 0 to 100 degrees Celsius in this case. So 100 Kelvin change, Celsius degree and Kelvin are the same size temperature. And when you use the MCAT formula and multiply everything out, you get 50,996 joules, and changing that to 3 sig digs, that's 51.0 kilojoules. Finally, you are going to boil the liquid water, change it to a vapor, and when you do that, you will use the simple mass times delta H of vaporization formula, and you will get to 3 sig digs 275 kilojoules. If you add all 4 of these numbers together, you end up with 368 kilojoules for the 122 grams. It's a lot of heat. Now, when we're talking about the attraction between molecules, it's useful to think of a potential energy well. So this is a well under the influence of gravity. And if two bodies attract each other, the potential energy will decrease as the distance shortens. The attraction will be high here. As they get closer together, the potential energy decreases, and you see those numbers going down on the vertical axis. And then there is a optimum distance, that separation distance between the two particles. If you get them any closer, they'll begin to repel. It's most useful to think about these as two atoms together. Now, if we consider liquids and solids, we are working with forces of attraction, keeping the liquids together in a kind of a random order, and in the solid, of course, they're held together in a matrix, a crystalline lattice. So let's look at the 3 kinds of intermolecular attraction that we find in liquids. And you can see here that the weakest is London dispersion, which is the attraction of weak random dipoles between molecular substances. The energy well, looking back at our analogy we just went through, is very shallow because the force of attraction is shallow. The strength of attraction is weak, and this is typically found in hydrocarbons in organic chemistry. The second, and therefore higher, force of attraction is dipole-dipole. When a molecule is polar, water being a great example of that, hydrogen chloride another one, there's a partial charge on each end of the molecule which attracts the opposite charge on the next molecule. These energy wells are also quite shallow. The strength of attraction is weak. It's stronger than London dispersion. Ketones and esters have this type of dipole-dipole attraction. Look for a C double bond O, and you will find a ketone or ester, as long as there's no OH attached to the carbon. And of course, the highest intermolecular attraction would be hydrogen bonding, which is a special kind of dipole-dipole force between a acidic hydrogen, in other words, a hydrogen that is able to be attracted to a electronegative element in another molecule, and the lone pair of that molecule. The energy well here is moderate, strength of attraction is moderate, and we find these, for instance, in alcohols and carboxylic acids in our organic chemistry. In solids, intermolecular attraction is similar, with some additions. In this case, you would have London dispersion and all the others, but you also have ion dipole forces, as for instance if you've got sodium chloride dissolved in water is a good example. Here we have a charged molecule being attracted by a polar molecule, or an ion is kind of a charged molecule being attracted to, say, one end of the water molecule. These energy wells are moderately deep. The strength of attraction is fairly high, and so this is how salts dissolve in water. The attraction of the positive end, the cation, for the negative end or oxygen end of water, for instance. And finally, of course, the highest form of solids attraction is the ion-ion force, where you have a positively charged ion attracting negatively charged ion. It's a very deep energy well, and the strength of attraction is high. So any salt, any oxide is going to have that type of attraction. This is a vapor pressure curve, and specifically for water, and it shows the temperature and pressure line where liquid and vapor are in equilibrium. You're familiar with that from even first-year chemistry. Water and vapor are in equilibrium at every point on this line. So this is a temperature pressure plot, and so at this temperature and this pressure, both liquid water and water vapor will be in equilibrium. To the left of these lines, all temperature and pressure values are valid for liquids, and to the right of the line, they are valid for gases. So if you see a diagram like this and you're given a point either here or here, you're not looking at equilibrium, you're looking at either here, it's a liquid point, here it's a gas point. And at the triple point, solid, liquid, and gas are all in equilibrium. We see here a complete phase diagram for water that includes the triple point. We get a diagram like this. This is a complete phase diagram for water, at least in the types of pressures and temperatures you're likely to see. This slant back is exaggerated. The angle is not nearly this extreme, but it shows why the high pressure under an ice skate blade can make the solid ice turn temporarily to liquid, so you have a good lubrication between the blade and the ice. That again is way too slanted back. Ionic bonding results from the net attraction between oppositely charged ions that are closely packed together in a crystal lattice. For instance, you see here sodium symbolized by the violet and chloride symbolized by the green. You have equal numbers of plus and minus charges. The size of each ion determines the kind of packing arrangement, but you do not need to memorize the packing arrangements from any textbook. The cations and anions in an ionic crystal, such as the one you saw, are arranged in a systematic periodic three-dimensional array that maximizes the attractive forces among the cations and the anions together, while minimizing the repulsive forces between cation and cation, or anion and anion. Remember from first semester, the Coulomb force is the strongest force outside of those that operate within the atom. This force is so strong between ions that ionic compounds tend to form very strong solid lattices. The vast majority of ionic compounds then are solid under normal lab conditions because the solid state maximizes attractive forces and minimizes repulsive forces. So ionic compounds have very deep potential energy wells, and you can see that the melting points and boiling points are very high because of the amount of energy needed to shake these apart. They are, therefore, very low energy level compounds. Coulomb's law describes the force of attraction between cations and anions in an ionic crystal. The force is proportional to the charge on each ion, so larger charges lead to stronger interactions, and if you're thinking in terms of the distance effect, the force is inversely proportional to the square of the distance between the centers of the ions. Therefore, stronger attractions can be found between the smaller cations and anions. We know about metallic bonding and the sea of electrons. You should familiarize yourself with that and use it to explain metals' low melting point, malleability, ductility, electrical conductivity, and low volatility.